Okay, so let's continue talking about Chapter 9. Now we're going to move on to Section 9.4. And just like we did with Chapter 8, remember we did hypothesis testing for the population mean, mu, and then we moved on to a proportion, and that's P, where P is the probability of drawing a success from a population of data that either has successes or failures in it of some kind. So we're going to do the same thing here, except we're going to consider two populations. Okay, so the first thing we'll have to think about is what do we mean by two populations? Well, they can both have a success or a failure. Since they're two different populations, we might quantify what a success or a failure is in both cases differently, but the point is that both of them will either have like a yes or no outcome, a 1 or a 0 if we're coding them to variables. So we can count the number of successes in our first sample, and we can count the number of successes in our second sample. We'll call those x and y, keeping with tradition. Then if m and n are the sample sizes, we can think of x over m as the point estimate for the number of successes in our first population, and then y over n is the second. And once we have both of those, they're approximating the true proportions, which we'll call P1 and P2. And the difference of P1 and P2 is estimated by using our data as x over m minus y over n. All right. And if we regard the samples as independent, then one of the two samples implies that x and y are both independent. Okay. So let's continue thinking about these populations a little more carefully. Remember that every time we've talked about P and P hat, the point estimate for P, we've had to think also about, well, when can we assume that a Z distribution really does give us, maybe it's the confidence interval or the hypothesis test. These are the considerations we always have to keep in mind. Let's say that the total population is M or capital N. All right, then our sample size can't be too large because otherwise we lose the ability to sample without replacement. Right? We want to sample with replacement, and remember that's what happens if we have a fixed quantity of things in our population. We sample from them. The chances of getting a success is fixed as P, but then if we pull something out, P changes a little bit. So if we sample more than 5% of our population, we can no longer assume the probability of a success is still P. So 5%, that's important. That gives us the assumption that we have a binomial distribution. And of course, that's what everything is built upon. Now, once we have a binomial distribution, in this case, we're going to have two binomial distributions. So now P1 hat and P2 hat are point estimates for P1 and P2. Their expected value in general will be exactly P1 and P2. Right? Now, the other thing when we standardize and get a Z variable, we always need the variance. So this is where, again, independence of the two samples come in. And when I do the variance calculation, I can separate everything out again. Remember, this was for the population mean. This was sigma 1 squared and sigma 2 squared. These are the variances based on a binomial distribution. Okay? And recall, just in case you have forgotten, Q is 1 minus P. But here we have Q1 and Q2 because we have a probability of success for P1 and for P2. So a lot more notation here. Okay, fairly complicated. But let's continue and look at a hypothesis test then. All right. This whole thing is drawn out just to say I have two different samples. I've got a population with a proportion of success P1 and P2. I think the difference is delta naught. Okay, and we're actually thinking usually delta naught is 0 because when we have delta naught is non-zero, things are going to get a little bit more dicey. So we're going to actually mostly focus on the case where delta naught is 0. Okay, when that's the case, we could alternatively just say our null hypothesis is that the proportions are equal. Okay, and in that case, we can simplify a little bit. If they're both equal, then why do we need P1 and P2? Let's just use P again. Okay, and that's nice. When the null hypothesis is true, we can do this. So what does our sample statistic look like, our test statistic? It looks like this, right? We've got P1 hat minus P2 hat. We're subtracting the null value, which is just 0, so it's omitted. But then this variance here, this is coming from, again, assuming that PQ is P1Q1 and P2Q2 simultaneously. In other words, from that last slide, if we were to look at the variances and just remove the subscripts, you could group them, and you get this variance here. Take the square root, that's the standard deviation. So this is going to be our test statistic when the null hypothesis is true. So let's take a look at what goes into constructing the test statistic. Okay? There's always one complication that we see when we do sample proportions compared to sample means, and that is the fact that the denominator always depends on p, on the one parameter that we have. Okay? So we would love to construct this test statistic and get a good guess for what p is, but this is telling us we need p ahead of time. So how do we handle that? Well, the answer is that we don't use the true p and q, we approximate them. But because we're assuming the null hypothesis is true, we could use either the x sample or the y samples to approximate p. So which one do we use? Remember, we had this same sort of a question very briefly in section 9.2. We talked about a pooled variance for the two-sample t-test, where, well, which s do I use to approximate my standard deviation? Is it S1 or is it S2? And we decided back then the answer was both. So we're going to do the same thing here. I'm going to use P1 and P2 hat to approximate P. Okay. Now, you could do a lot of different things. You could simply average them, just take half of P1 plus P2. The natural thing to do is notice that if we assume that P1 and P2, both proportions are the same, that means that both of our samples have the same probability of success. So X is a certain number from my first gathering, Y is another from my second gathering, but they both have the same probability of success. So when I take X plus Y, well, gosh, that's just another binomial variable with a larger sample size, but the same probability of success. That's the key to it. So instead of thinking about X over M and Y over N as separate things, we just think about X plus Y as one thing and M plus N as the other thing. You could always go back and write this. Yes, it's technically an average of P1 and P2. But we just want to replace this P right here with this quantity then. That's the whole point. So now we do have a way of actually forming our test statistic. Okay? Even though P was sort of needed to estimate the difference of P. So now that we have that in place, let's proceed. Okay, this is again our usual slide where all the information is gathered, and a lot of it's almost identical. Here's our test statistic as just laid out on the last slide. P hat, there it is as a reminder. It's written a little bit more compactly just so it'll fit on the slide, but you could verify the algebra is the same exact thing. And so we can do hypothesis testing for two proportions. Here's a recent article that was reporting 549 participants who regularly used aspirin after being diagnosed with colorectal cancer. And there were 81 colorectal cancer-specific deaths. Okay, so that's one set of data where we have a proportion of 81 over 549. But similarly, we saw 730 people who did not take aspirin, and of those, a certain other proportion have, died of colorectal cancer. So let's take a look at these two proportions and see whether or not they're any different. Okay, and of course, if this study is a controlled experiment, then we can infer that the difference between the two proportions, if there is one, will be caused from the aspirin. So let's do a hypothesis test to see whether or not aspirin actually helps the incidence of colorectal cancer. So let's lay this one out very carefully. Let's do the 7-step procedure. The parameter of interest is P1 minus P2. That's going to be the difference in proportions of people that died of colorectal cancer from those who use and do not use aspirin. The null hypothesis, I think the proportions are equal. Let's see if I'm right. The alternative hypothesis, well, we would like to study whether or not the incidence goes down with aspirin users. So we'll do a lower tail hypothesis test in this case. And before having any of our sample data, notice here, this is sort of interesting. We don't have any numbers to plug in yet. We don't have p hat, which is based on sample statistics. We don't have p1 hat or p2 hat. Those are based on sample statistics. So, in general, this will be our form, but we're still waiting for our data. So in step 5, let's introduce the data. Okay, going from the last slide, we had 4 numbers to plug in. What were they? 81 over 549 and 114 over 730. See how well my memory is here. 141 over 730. So we'll plug those in. We'll have P1 hat, P2 hat, right? You'll take the sum of 81 and 141 and divide that by 730 and 549 to get P hat, okay? But anyway, when we do all of that math, the Z statistic we get is negative 2.1317, okay? Now, what do we do with that? We construct the p-value, okay? And for the lower tail test, what does that mean we do? We take and plug into the normal distribution. In Excel, you can use norm.s.dist and just give it this number. Or if you're going to Minitab, you can use calc probability distributions and go to the normal z-test. And we don't have to do anything special once we get that number in this case because it's the lower tail test. That's the nice one. So here's our p-value. And what does that mean? It depends on the significance level. So normally we think about 1% or 5% significance level. If we have 5% significance, then the p-value is smaller than alpha, than 5%. And so in that case, we would reject the null hypothesis. In this case, we would reject the claim that P1 and P2 are both equal, and therefore we're actually saying P1 is less than P2, and that means that aspirin is actually reducing the incidence of colorectal cancer. Now, of course, if we have a 1% significance level, that means we're being a little bit more careful with our data. We don't want to make an error in our conclusions, so we would instead accept the null hypothesis and say, well, I need a little bit more evidence to be compelled that aspirin's actually working. Okay, so that concludes an example for looking at hypothesis testing. And remember, there's always 2 things we can do with such tests. The first is to just use data to figure out whether or not we think a hypothesis that has been made is true. The other one is, let's design a test that has a certain level of power. We want to make sure that we're actually getting the right answer. And usually we think about this in terms of trying to detect a difference from what the null hypothesis stated. In this case, if we were thinking of a hypothesis like this, where I think the proportions are equal, the alternative hypothesis is that they're not. And to figure out whether or not we can detect some other value, we have to first decide what that other value might be. So let me use D to denote the difference in the proportions. I think that maybe P1 is 20% and P2 is 30%. So I think D is 10 or negative 0.1 in this case, right? So our statistic that we'll be interested in will be of this form, and we have sigma just as before, okay? And these are the tests that would arise if we considered all the different scenarios. A lot of very compact notation here. Again, the whole point is that we really want to use statistical software to do tests like this, but they can be done by hand if you really desire to do so. I would recommend, honestly, to just use the software to do a test like this. But here's the details if you choose to do otherwise. They're still based on the z distribution. And if we have a given sample size, we can decide whether or not we have a certain power of our test. Remember, beta is the probability of not detecting D when we should have. We assume the hypothesis is true when it's not. Okay? And 1 minus beta is the power of that test. And then likewise, if we're given a certain alpha and beta, significance level, and therefore a power is determined, we can figure out a sample size to guarantee that our test is accurate. So let's look at, really quickly, an interesting example. This one is not really just designed to look at sample sizes, but the whole process in general. This is a famous example. Let's look at what happened when the polio vaccine was first introduced. So, a great success in modern times, of course, eradicating polio, and vaccines were required to do that. But of course, at the time, vaccines were very controversial, and it was still not decided whether or not the vaccine was going to work. So this is what happened. Some brilliant statisticians of the time set up a control experiment. Okay, so they had two groups of children, selected randomly which of these children would go into the placebo group and which would get the actual vaccine. And let's see, neither the individuals, yes, double-blind experiment we call that, right? So that not even the people administering the shots knew, and therefore there's no danger of the placebo effect actually happening. So that just guarantees that our data is sound, controlled, random data. And of course, in this case, we're going to have which proportion P1 and P2 of children actually had, in this case, paralytic polio, whether they were given or not given the vaccine. So this can be looked at in terms of hypothesis testing. I want to know if the proportion is different in the vaccinated versus the non-vaccinated group. Did polio incidence go down? If it went down, then this is my alternative hypothesis. I reject the null hypothesis and I say the vaccine is working. So, in order to do this, the first thing we have to do is sort of get a rough estimate for what we think P1 might be, and we're going to use that to fill in part of our test statistic. And this is required if we want to estimate what sort of a sample size we'll need to detect deviations. So just for a beginning discussion, let's suppose that before any vaccine was administered at all, we have a rough estimate of how many children actually have paralytic polio, and it's 30 per 100,000. That's the incidence. Okay. Now, what we can do is say, I think that the vaccine is doing something significant, practically significant, if the proportion gets cut in half. Okay, if we can cut the incidence rate in half with the vaccine, that's good. So if we want to detect this difference, what sort of a sample size would we need to do so? So D is going to be the difference of these proportions, 0.00015. So let's suppose that we have a given significance level and a given power level. Remember, if the power is 90%, that means beta is 10%. Okay. Assuming equal sample sizes, we plug into the formula from the last slide. Again, wouldn't highly recommend doing this by hand, but it can be done. But as you can see, we get a really large number. We need several hundred thousand children to look at an incidence rate like this. Remember, this is M and this is also N, so we'll need to double that to actually do the full study. This is actual data from when the study was done back in the 50s, and the numbers we're looking at are the top 4 here for paralytic polio. We have all these other numbers, and if you're really interested in the data, you feel free to look. There's some footnotes that sort of guide us into what happened. As you can see, false reports were also included in the study, so everything is fully explained there. But we're going to focus on just this small part and do a hypothesis test for it. So let's pull over the relevant data. For the placebo group, 201,000 patients were actually examined, well over the 170,000. So we have a very nice, powerful test. We're going to know that P1 and P2 are different if they in fact are. So the incidence rate for the placebo group was 115. For the vaccine group, roughly the same sample size, but the incidence rate is already quite small. So this is looking well so far. So let's compute the actual numbers. And P1 hat, okay, we're just going to take X over M in this case. We're going to take Y over N to get P2. All right. Now, how do we get P hat? Remember, we're going to need that for the test statistic. P hat is the sum of these two divided by the sum of these two. We're assuming P1 is equal to P2, so we've really sampled from the same binomial distribution. So P hat is just the sum over the sum. Right? The sum of these two over the sum of these two. Q hat is 1 minus that value. And now we have the 4 quantities. If you go back and look at the test statistic, we can plug everything in. So P1 hat minus P2 hat over P hat, Q hat, and this is 1 over M, and this is 1 over N. That's everything. And if you look at this test statistic we have, that's a z-value, and it's 6.7. By far the biggest one we've seen in this class, I think. Right? Normally we get something like 1 or 2, maybe 3, 3.5. Okay? By the time we get to 3.5, the p-value is pretty small, essentially 0. With this value, I think if you were to actually compute the full p-value, maybe go to Excel and just drag open the cell and see how many zeros you have, there's probably 8 or 9 zeros. This p-value is 0 at any and every significance level. We have to reject the null hypothesis. So, because of that, the vaccine was judged a resounding success. This is not due to statistics, this is not due to randomness, this is because the vaccine actually worked. Okay? So this was a great example of a modern-day triumph of statistics to use one of these tests that we're learning about to show something like, yes, the polio vaccine will work. And then after this fairly small trial was set, millions of lives were saved. Okay, so let's also look at a confidence interval for population proportions. Just summarizing it here, so it's all there if you want to look at it, but it's quite terrible, honestly. There's a lot of different parameters. We've got P1 hat, P2 hat, and the Q values. Remember, Q will be 1 minus the corresponding P, right? And so the lower bound and the upper bound of the confidence interval are given in terms of a z-score, okay? And we always have these little issues to concern ourselves with for what happens when the sample size is sort of small. These confidence intervals, they're not as reliable, and some research has been done into modifying these results, but we're actually not going to tackle that too much. One suggestion that has been made is just add a little bit to the sample sizes, and this tends to remove bias for small samples. But again, we won't concern ourselves too much with this. There may or may not be, I forget, if there's a homework problem that uses this, but if it does, then this is what they're talking about by modifying P and Q, P1 and P2. Okay, so that's a confidence interval. Let's take a look at how this works in practice. Okay, recent experiment to compare treating cancer patients with only chemotherapy, or maybe they use chemotherapy and radiation. How does that look? So we have two different samples that we're interested in. They took 154. I believe if we look down below that this is women who are being treated for breast cancer in this case. Let me see here. Yes, so radio chemotherapy, breast cancer. Yes. So these are statistics. Does it help to, in addition to chemotherapy, also give radiation treatments for women? So we look at the proportions. Okay, 76 of 154 who just had chemotherapy had remission, I think, yes. Oh, survived at 15 years. So yes, in the remission, okay. 49.4%, okay. And for the combination of the two, we see 60%. It's a little bit higher, so maybe there's something to that. So in this case, we're not necessarily just going to be interested in whether or not 0 is the true proportion difference, okay, that the proportions are equal. Let's build a confidence interval around what the proportion really could be. Okay? What if we took the proportion of all women who survived cancer just with chemotherapy, and the same for those who had radiation as well? Right? Are those true proportions very different from the ones we see in our sample? Here's what we know with 95% or 99% confidence. Okay, using the formula from that last slide, we would compute these two figures here. And if you look, it's mostly negative, but 0 is in that confidence interval, so we can't necessarily say with full certainty that, that this is really any difference. I mean, it's suggested that there's a difference between adding radiation to the treatment, but we don't quite have enough statistical strength to say that that's true conclusively. Okay, so that wraps up section 9.4, and we'll take a little break and we'll go for section 9.5.